All right, let's go over example 3 and question 4, I think it is. Yeah, anyways. What we have here in this first example is a sled that's being pulled horizontally, and then we have an angle of the sled. So it's being pulled at an angle horizontally. And we're asked to figure out how much work is done by the sled. Now, though the work formula looks very simple, it does have that one thing, that very important thing we have to keep in mind, and that's the fact that the force and the displacement vectors need to be in the same direction for it to work. So we can't just multiply 15 times 4 because the 4 is in the horizontal direction while the 15 newtons is up at that angle. So in order to get this correct, we have to either find we have to figure out how much force is in the same direction as the displacement that occurred. So in order to do that, we need to break down the 15 newtons into its two component parts. So essentially we're making a triangle out of this, and we need to find the sides of that triangle. Now the only side that matters to us is the one that's in the same direction as the displacement. So it's going to be this horizontal one down here. Now in order to do that, we just need to, looks like that's a cos. So cos of 30 is equal to the adjacent, which is what we're looking for, over the hypotenuse, which is 15. If you solve for x, you get 12.9 newtons. And then once you have that 12.9 newtons, then you just need to plug it into the formula, and it's pretty straightforward from there. 12.9 newtons times the 4 meters traveled. And if we do that, we get a work of 52.0 joules. So that's how the first example is done. It's straightforward once you understand the trick that the force and the displacement need to be in that same direction for it to work out. Now, for question 3, what we have here is a 100 Newton block that's being placed on an incline. It's frictionless. Draw the weight and the normal force vectors acting on the block. So I always like to start where the center of the block, where it connects to the ramp, not actually the center of the very center of the block itself. I find it makes it a little bit easier. Draw my arrow straight down, and I like to make sure it passes through the bottom of the floor. I think, again, that just makes things a little easier to see how things work. And then the trick is you want to connect from the bottom up to the incline so it hits it at a 90 degrees. And that does take a little bit of practice to do. The arrow for that goes down, and then we can connect the force over there. Now, why we're breaking this up, this is FG, by the way. Oops. Excuse me. Why we are breaking it up like that is in the future that's going to become necessary to know what each of the parts are. The part going down the ramp and the part being held up by the ramp. And that's also asking us to draw the normal force as well. That's going straight up. And the thing about the normal force, it's the same as the part of the weight that's being held up by the ramp. So those are equal to each other. Otherwise, the block would be falling into the ramp or would be rising miraculously up in the air. It's doing neither, so they cancel each other out. The next part of this says determine the force necessary to move the block up the ramp at a constant speed. So the force that moves up at a constant speed, if you're moving at a constant velocity, the key thing there, constant velocity, should mean equilibrium. All the forces are equal out. So right now, this force is balanced out by this force. So we need something to balance out this force going down the ramp, the fact that it wants to slide down the ramp. Since there's no friction, the only force that we have is some kind of applied force holding it upwards. Oops, meant to be an A there. That's Fn, I didn't label it before. So that applied force going up is the one we need to calculate, and it needs to be the same as the force of gravity going down. So in order to find that, we need to figure out what this is, and if we figure out what this is, it's going to be equal to that. So we have the 100 newtons going down. We have the 30 degrees there. Keep in mind that that 30 degrees transfers right over to here. And then from there on out, you just need to calculate that. Looks to me, don't forget that this long one right here is the hypotenuse. So it looks to me that we should be using sine here. So sine of 30 is equal to the thing that we're looking for divided by 100 newtons. And because sine of 30 is 0.5, my x is just 50 newtons. So the 50 newtons is the force that's gravity's pulling it down at, which means that's the same as the force we have to pull it up at as well to make sure it's moving at a constant speed. Okay, now for this next one, I don't know why all my marking stayed over. If a block is moved 2 meters along the path, how much work is being done on the block? Okay, so I'm going to do that over here. Oh, it vanished this time. So we have a block 2 meter along the plane of this force. So that means that it's saying it's in the same direction of the force. So from there, it's a classic work formula. Because it's in the same direction of that force, we don't really have to worry about direction here. So that force was 50 newtons times the 2 meters. And so we get 100 joules of work being done. So that last part is pretty straightforward. The biggest problem with ramp-based questions is worrying about the angle and how to properly draw the forces. So really part A of this question was the tough part. From there on out, it's more straightforward, more what we're used to. Do note that a lot of work questions with ramps are actually much more straightforward than this. They often give you that force going up. And the thing they tend to test you on is for you to know that the force up the plane, you should be using also the distance up the plane, using the force and the displacement that are in the same direction to figure out the work. So that's generally the test that they try to pull for a work-based ramp question, but this one was more of a classic force ramp question. That's pretty much it. Again, if you have any more questions, always feel free to comment or email me.